objects will remain in orbit for centuries.
Wow. Well, to answer Jennifer's question then, is anyone working on cleaning up space junk?
Well, because things eventually fall back in space, there's no plan right now or projects that are on the way to clean it up. I mean, the nature will take care of it if you want, particularly in lower Earth orbits. And on top of it, because it travels at such a high speed that you cannot catch it, there is no plan to clean it up. What we are doing, however, we are also, on the longer run, considering projects where you would have small robots that would be sent and would be able to capture the bigger piece. So satellites that are no longer operating but are nevertheless up there floating in space, if you want, but are no longer being used. So this little robot would go there, grab it, and bring it back to Earth.
Okay, now on to Mark's question. Why doesn't the space shuttle bring back junk to Earth when it's returning with an empty cargo hold?
Yeah, well, again, the debris, you would have to be able to catch it. So given that there are not too much debris up there, it would be useless for the space shuttle to try to grab some of these debris. It's the probability that you are going to encounter a debris while the shuttle is orbiting is very small. And again, even if you were to encounter one, you wouldn't be able to catch it because of the speed at which they travel.
It would go right through you.
Yes, absolutely.
You need a heck of a catcher's mitt to do that. Mr. Gilbert, thank you very much.
It was a pleasure.
Hugues Gilbert is Director of Policy and External Relations at the Canadian Space Agency in Saint-Hubert, Quebec.
Hi, my name is Barbara Lovies in Vancouver, and my question is, what food did woolly mammoths and mastodons eat? If it were possible to clone a mammoth and bring it back to life today, would the food that they ate still exist?
For the answer, we dug up Dr. Grant Zazula, a paleontologist with the government of Yukon in Whitehorse. So, first of all, Dr. Zazula, what's the difference between a woolly mammoth and a mastodon?
So a mammoth is essentially a great big grazing elephant, and their teeth have these sharp ridges but are generally flat. So they're basically for grinding large quantities of grass. They need to eat lots of hay, and their teeth are completely different from a mastodon, which has evolved through time to be a browser. It eats small trees and shrubs. It has really high cusps that are used for breaking branches. So very different teeth morphology that correspond to their diets. So if we think of a mammoth, it needs to consume a huge amount of hay, basically, grass to keep it going throughout the day. It's generally thought that they could probably consume between 400 or 600 pounds of hay during one day, or grass and yeah, mostly grass, small flowering plants like poppies and buttercups and cinquefoils. These are all the kind of things that have been found within their stomach contents.
Wow. So they're both basically elephants, hairy elephants, but they just have different diets.
Yeah, essentially, if you use the modern day analogy, a mammoth would be a cow, and a mastodon would be a moose.
Oh, now, did they look the same?
Well, they're quite similar looking, except for some different morphology in the way their back is sloped. But I think the key difference between mastodons and mammoths is, given that they ate completely different things, they probably lived either in very different environments or at different times during the Ice Age. And we generally consider mammoths to represent probably the keystone herbivore during the cold, most harsh glacial times during the Ice Age, when there was windswept grasslands that are covering the north, Alaska and Yukon. So they were wandering around eating hay, and there was probably very few trees around at the time. But during the Ice Age, there's these little interludes where we have climate return to basically present-day conditions, and we call those interglacials. And we see the boreal forest return to the north, and that's generally when we assume that mastodons are living in the north.
Now, your description of what they ate was quite detailed there. How do we know that?
It's actually the fossil record of these ancient elephants is actually really good all across the Americas and especially Siberia, where we have a number of preserved fossil carcasses that have been found throughout the last couple centuries, actually.
Carcasses?
Yeah, like complete bodies of these things have been found within the permafrost, where there's skin and muscle and internal organs, and we can actually pull out an entire freeze-dried mammoth. And this is especially true in Siberia. And there's one mammoth that was found in Siberia near the turn of the century, where it had over 650 pounds of hay in its stomach. So by looking at the plant remains, we can really get a good detailed reconstruction of their diet and also the plant communities that were living in the area at the time.
Okay, well, let's get on to the second part of Barbara's question. If a woolly mammoth were cloned today, would there be somewhere where it could find suitable food?
Yeah, it's one of these questions that has a lot of answers, because not only is this a scientific question, it also becomes a whole ethical issue. But just to think about a mammoth being this great big grazing herbivore, we could probably have mammoths living today in maybe the southern steppes of Russia, or even in some of the grassy areas of the foothills of the Rocky Mountains, like places that get cold in the winter but have large expanses of grassy vegetation that they'd probably do just fine in. And that brings into the whole question of, why don't we have them today? And if we do bring them back, how are they going to live? And if we can clone one, where would we put it? It would be a solitary animal, or are we going to bring back herds for them to live with? And where would you put it, in a zoo, or try to put it in its natural environment? One of the issues about trying to put a extinct animal back into the world, in the natural world, is it no longer has the same kind of predators. So if we brought a mammoth, cloned a mammoth, and put it in the foothills of the Rocky Mountains in Alberta, are we going to bring back Ice Age lions or African lions to hunt them, to keep their populations in check? So it's an ecological, ethical question for sure.
Interesting stuff. Dr. Zazula, thank you very much.
Well, thank you. That's great.
Dr. Grant Zazula is a paleontologist with the government of Yukon in Whitehorse.
Hi, this is Larry Bissonnette from Ottawa. I was dining at a restaurant and the ice cubes in my glass were completely clear. How do they do this? Thank you.
With a perfectly clear answer is Dr. Marianne White from Dalhousie University in Halifax. So first of all, Dr. White, why are my ice cubes at home always cloudy?
Well, the cloudiness is an indication that ice is not just pure water. And when you freeze the water, the other component, which is air, settles out of the lattice, doesn't fit into the ice lattice, and has to go somewhere else, and that forms those little bubbles that we see as cloudiness. So that's air in there.
Well, why do the air bubbles make it look white?
They make it look white because they're scattering light. Where it's very pure ice, it's quite transparent and the light can go right through. But where you have those little beads of air pockets, the refractive index is different and the light gets scattered.
Okay. Now, can you make blocks of clear ice in the laboratory?
Yes, I can. And the way I do that is by degassing the water or de-aerating the water. And we do something that's called a freeze, pump, thaw cycle. And what we would do is put the water in a container that's shaped like a test tube and freeze it from the bottom. And as it starts to freeze, the air goes preferentially into the water above, and we pump on that with a vacuum pump. And we freeze all the way up, excluding the air, and then we thaw it and let it equilibrate, and do that again several times. And we eventually remove most of the air. And then when we freeze the water to make ice, the ice will be very, very clear.
Boy, that sounds like a complicated way to do it. Now, getting to Larry's question here, what's the restaurant secret? How do they do it?
Well, I think what they're doing is they're using a slow buildup of ice. They're allowing the water to flow continuously and building up the ice in layers. And as the ice is being built up, it's again expelling the air from it and forming just the clear ice structure with no air pockets.
They have machines that can do that?
Yes, this is a very fancy thing to have. It's not your regular freezer and tray of ice cubes situation.
Oh, okay, so making it in layers, now how does that keep the air out of it?
Well, it spits the air out, you might say. As the lattice is being formed, the ice lattice, it's spitting out the air molecules that don't fit in there. And if you're only doing it a little thin layer at a time, the air can actually escape.
The other place where I've seen clear ice is icicles.
Yes.
So how do they do it?
They do it similar to what's happening in the restaurant. An icicle that is formed by very slow dripping and slow layers of buildup has an opportunity, again, for the air to be expelled as it's being formed. So, in fact, by looking at the icicle, you can tell something about the situation, the history of the water, how quickly it is frozen.
Boy, so thin layers are the secret here.
That's right.
Freezing. So how can I make clear ice at home?
Well, if you go to the internet, you'll find that if you start with boiled water and that will expel some of the air and freeze slowly, then that will make clear ice cubes. But I have to tell you, the last several days, I've made tray after tray of ice cubes at home, and I have not been successful in making very clear ice cubes. They've always been, no matter whether I've used water boiled for a long time, water boiled for a short period of time, water boiled several times, water boiled and then cooled, or directly hot water boiled and then put it into the trays. I've tried everything, and they all look the same as water straight from the tap making ice cubes.
Oh,
and
no.
I think that's because my freezer, having now studied this thoroughly, freezes the ice cubes from the outside in. They form a top and sides and bottom, and that traps the air, and the air doesn't have a chance to move. The ice pocket, the cloudiness, is always in the same location about 2/3 the way down of the ice cube, and that's the same no matter what. So I think that's trapping it in, and it's the freezing mechanism. Again, in the lab, if we freeze from the bottom up carefully, then we can get clearer ice cubes because we're expelling the air.
Blame it on the freezer.
Yes, I'm going to blame it on the equipment.
Did you try distilled water? Would that work?
They say distilled water is better because of the lack of salts and the lack of cloudiness that the salts would also bring. But I am not a proponent of drinking distilled water, and of course you're going to drink something from the ice cubes as they melt. So I didn't try that one. Although I had distilled water at home, I didn't try it.
Okay, but the answer to Larry's question, it's all in the equipment, and freezing the water layer by layer, getting the air out, will give you clear cubes.
Yes, sir.
Dr. White, thank you very much.
You're welcome, Bob.
Dr. Marianne White is a professor in the departments of chemistry and physics at Dalhousie University in Halifax. I'm Bob McDonald, and you're listening to Quirks and Quarks, the national science program heard every Saturday afternoon and Monday evening across Canada on CBC Radio 1. We're live on the internet at cbc.ca, across North America on Sirius Satellite Radio 137, and on various public radio stations throughout the U.S. Coming up next, Little Boat in a Big Sea.
Hi, this is Murray Sovereign calling from Squamish, BC, and my question is, if you had been in a small boat on the Indian Ocean on Boxing Day 2004, directly above the epicenter of the quake that caused the tsunami, what, if anything, would you have experienced?
Joining us with the answer is Dr. Richard Thompson from the Institute of Ocean Sciences in Sydney, British Columbia. So, first of all, Dr. Thompson, just in general, what happens when an earthquake's epicenter is located under the ocean?
Well, there's two parts to this question. One is there's energy radiated out from the earthquake epicenter itself, and then there's the displacement of the seafloor that's caused by the earthquake. And in the case of the 2004 Boxing Day earthquake, it was this displacement of the seafloor that caused the devastating tsunami.
So what happened to the seafloor during that quake?
Now you got to remember, this is one of the biggest earthquakes that's ever been recorded. In fact, it was the second largest ever recorded.
Really?
So yeah, there was a huge rupture along the seafloor, 1,200 kilometers of rupture, about 100 kilometers off the west coast of Sumatra and the Andaman Islands. And so this rupturing, which started off fairly slowly and then speeded up to about 2.5 kilometers per second towards the north. And this rupture caused the seafloor on the western side to lift up about 12 meters in segments, and the eastern side to fall down about 5 meters. So we had, within a relatively short period of time, a displacement of about 15 meters taking place.
Wow. So one side of the crack went up, the other side of the crack went down. So that's what happened on the seafloor. Now, what happens to the water above that when you get that much motion on the seafloor?
So this depends on the water depth. So the deeper the water you're in, the less effect it's going to have, because as this seafloor is being displaced upward and downwards and lifting or pulling down the water, if the water is deep enough, the water can escape to the side, so it spills to the side, so it cushions the effect, so it's not felt so much at the sea surface. As you get in shallower and shallower water for this kind of disruption,